We had quite a few people wanting to come in person. We ran out of registration because of room capacity limits. So subscribe to the calendar, be the first to come. And for more updates, sign on to the WhatsApp channel. Here we'll be posting all decentralized AI updates from MIT. And this is our program on decentralized AI, which has 7 main aspects. If you're interested in this, please email rosker@mit.edu. Next, I'll be passing the torch to Abhi.
Awesome. Thanks everyone for coming here. And we have an exciting speaker lineup. So I'm not gonna take too much time, but I quickly gonna present some of our work in decentralized AI and focus on 3 interesting aspects. And those 3 are why decentralized AI, why now, and then how do we go about doing it. So let's start with why. I think as we have heard in the Ramesh's talk already, there are plenty of problems in centralized model, but I want to provide another perspective here. So I'm gonna start with this very humble claim, as you can see, intelligence equals to scale multiplied by heterogeneity. And what I mean by that is, first, let's look at scale. So we have seen plenty of evidence in empirical evidence. When we increase compute, we see reduction in test loss, which you can take as a proxy for how intelligent or how capable these models are. Then we have seen also similar phenomena as we increase the data set size, this test loss goes down again. And then finally, number of parameters in these large models, as we add more and more of them, once again, this capability of these models really go up. So clearly scale is very useful. And on all on all these 3 dimensions. But there is another not so or somewhat underappreciated aspect, heterogeneity. So with heterogeneity, we have this phenomena of mitigating bias, improving robustness of these models, which is a big issue right now. And then we are also seeing robustness in architectural motifs in these deep learning models, in mixture of experts, multimodal learning, and so on. And by heterogeneity, I mean, again, multiple dimensions of heterogeneity similar to scale, heterogeneity of your data, and another way of saying it is data diversity. Also heterogeneity of parameters. Speaking of heterogeneity of parameters, we actually know without heterogeneity, we suffer from a lot of these catastrophic problems. In generative model, there's a phenomena called mode collapse, where the model will just output same thing again and again. And that's why it's collapsing on a single mode. We also see a phenomenon of neural collapse, also sometimes known as dimensional collapse in self-supervised learning. And then finally, poor generalization. So generally, the idea here is heterogeneity is good in data sets, models, and tasks to improve this capability, because scale is not alone going to give us all these interesting properties. Now, second claim, once again, is that we have got this trilemma. So in a centrally organized system, you can either get scalability or heterogeneity, but not both. And of course, it's a spectrum. So it's about increasing on both dimensions. And once you get rid of central organization, then you can start scaling a lot more and still be compatible with heterogeneity. If you don't agree with that claim, let's talk. There's no empirical evidence for this yet, but a lot of work has been done in this for societal cooperation. So another aspect, and the reason we want to get towards decentralization, is just because if we want to have these models be more capable, learn from lots of data sets which are diverse and heterogeneous, we need to give up this notion of centralization and make these algorithms compatible with distributed decentralized data. So that was more about the why. Now let's look at why now. So I'm going to argue that we are entering a very exciting time, and this is mostly reasoning by analogy. So we have looked at this era of mainframes, which eventually became personal computing, where everyone had these devices. And then once these devices were with individuals, the question was how to connect them and create information flow across these devices, and that's what internet and also cloud computing allows us to do. And you could argue the fact that internet exists and all this data exists on the web has led to all these interesting models recently. We are seeing a similar trend where we started with foundation models, lots of capabilities, and now we are entering this era of personal co-pilots, where these models will be used by individuals to improve their different aspects of lives. And then the immediate question is, how do we connect these co-pilots? And that's where we believe decentralized AI is going to come. So that's one reason for why now. But also to look at that personal agent's perspective, I'm going to argue that there are three emerging trends going on right now. So first emerging trend is this notion of AI PC and open source models. So lots of these PC companies are right now integrating NPUs or even small size GPUs in their PCs so that you can run these models locally. And at the same time, you're also seeing lots of open source models that you can actually run on your device. Some of you might have heard of llama.cpp and similar other examples, where all you have to just do is install this package and you are running a model locally. And we are seeing two trends simultaneously, which can be a little bit confusing. So we are seeing models are getting very big right now, but at the same time, we are also seeing a trend of these very big models getting shrink down to very small models so that you can run them on device. So it's more like this heterogeneous future, similar to how it happened in the case of personal computing, where you have very small devices, but at the same time, you have huge data centers running on cloud. So I think similar theme is emerging in the context of AI PC. And once those models are running on device, then connectivity becomes a crucial question. Second emerging trend is personal agent and tools. So far, what we have seen with these models is you give them some prompt, they give you the output, and then you use this output to do the task. But the whole emerging trend of agents is about how can these models do tasks on their own. And the way that happens is you equip with them tools. So once these tools and agents are part of this network ecosystem, then collaboration becomes an interesting problem. Because now you want to have these agents that can talk to other agents or access tools that are not available just on your local system. So the question there is, how do we enable collaboration among these agents as well as tools, and really create this access control layer so that you do not want to reveal every information to these agents or tools, but at the same time, you want to permit some information, knowledge, wisdom, and so on. And then finally, this idea of monolithic to polyolithic models. So what's happening right now is instead of relying on a single large model that will give you everything, right now we are seeing this trend of integrating these models with tools like RAG, so retrieval augmented generation, where it's connected to the database and it's using the database to improve its output. But not just RAGs, but also there is a lot of interesting work going on in integrating LLMs or any large models with planners, reasoning models, and so on. So it looks like that going forward, we will have not just a single model, but a whole ecosystem of these multiple tools or different models or databases with different capabilities that will augment each other. And then a very important question is, how do we orchestrate this flow of information? So think about like, how can we train these models collaboratively, or how can we even do distributed and decentralized inference? So these three emerging trends is why we believe decentralized AI is going to become more relevant and important. And then let me give a little bit of perspective on how to do it. So we have recently put out this perspective paper on decentralizing AI. And the way we are thinking about is this: there are two axes. One axis is decentralization, and the other axis is intelligence. And if you look at those axes independently, then obviously a lot of work has been done. And on the intelligence axis, you can see starting from something like retrieve, or you can think of it as storage. Then we go to compute, and then we finally go to learning. So in 90s or even after that, we had these really sophisticated systems that were relying on just pure computation to act intelligently, and these are called expert systems. And then now we are in this learning era where instead of programming intelligence in your code, you are just programming how to learn these primitives, and then you are seeing things like foundation models and so on. On the decentralization axis, we start from distributed data, distributed compute, but then also distributed organization. How many of you have used BitTorrent or any peer-to-peer file sharing service? So it's pretty powerful if you have used it, and like without relying on a single central server, you can still achieve the same capability. And imagine if you can build a similar BitTorrent or Napster for machine learning, where people with their own data sets or compute can participate and join this ecosystem. And a lot of work has happened, not in the context of machine learning, but for these decentralized systems to support that technology stack. So lots of cryptographic primitives exist, for example, and they have been getting very efficient in the last few years, especially in homomorphic encryption. And then blockchain, obviously, a lot of us are familiar with that and how it can serve as a foundation layer to build a lot of these things. So the way we are seeing these two worlds colliding together is by going on the intelligence axis and integrating with what already exists, or we might have to build for decentralized systems. And that's where comes the sweet top right corner. And the way we think about how to solve these problems, and you have seen a similar version in Ramesh's slide already. So we see these are like 5 important pillars that need to be addressed. And if we can address them together in a single system and create protocols, then we can really start deploying some of these systems at a very large scale and hopefully get adoption. So quickly to run through them, all of these pillars, we have privacy, very obvious. We want to protect information, but at the same time enable collaboration. And as I was saying before, tools like homomorphic encryption, you might have heard of differential privacy, which is a more of a statistical notion. We want to utilize those primitives. Verifiability becomes very important, especially when you're giving privacy to people, because now they can contribute anything. So to prevent those kind of malicious actors, we also need verifiability primitives, and then also prevent issues like free riders and so on. Incentives, obviously, when you want to enable participation from a large scale of individuals or organizations, once again, we need to build these foundational primitives so that collaboration could happen, and incentive is how people collaborate. Orchestration is something I'm most excited about personally. So if you think about internet, one thing that really enables this collaboration is the fact that there's exabytes or even more volume of data, but at any given point of time, all you need is kilobytes of data. So while all that information is present, having services like domain name routing, search, recommendation systems, and all these things enable you to get down to kilobytes you care about. And that way, everyone can upload whatever information they like to upload, and anyone can download what they want. So having similar capability, but in the abstraction layer of machine learning, where my model should be able to collaborate in this decentralized ecosystem of individuals or organizations based on what my data is and what tasks I'm interested in solving. And that's what we mean by orchestration, so that we can scale coordination at a large scale. Finally, crowd UX. So again, I'm giving a lot of internet analogy. So here the analogy is something like web browser. So internet clearly existed before, and web also existed before web browsers, but it was only or mostly geeks. I wasn't born, but that's what I've heard, who have been using it. And then web browser enabled people to participate at a very large scale and also contribute information. So in that sense, we also need similar web browser in the context of machine learning, and especially this decentralized machine learning. So yeah, that's the perspective. And then finally, another thing we highlight in our perspective paper. So this is actually a different paper, which really got plenty of press recently. So the paper is about building generalist artificial intelligence for healthcare. And they identify some critical challenges that need to be addressed before we can get to that point. And even though they're not talking about decentralized AI, turns out they identify these 5 challenges. And surprisingly, they map one-to-one with our perspective on decentralized AI. So first question is about validation of models on unseen data. And it's a big problem in benchmarking actually large models right now, that how do we know their performance on out of distribution or even data they have not been trained on. And a lot of zero knowledge primitives could be useful here, which is something we talk about in verifiability pillar. Verification of model decisions, as in how do we understand what information is coming in, interpretability, and those kind of problems. And that's something we aspire to solve in the pillar of CrowdX in decentralized AI. Social biases, I think if we are following the news on how these models are being deployed, we are well aware of all the issues. And here, creating this permissionless participatory system where a lot of individuals can participate by creating appropriate incentives is going to be very important. Privacy leakage, once again, pretty obvious. These challenges are all about like how can we train in a way so that these models do not spit out personal information, but not just training, but also inference, where if I want to type my symptoms and then send it to ChatGPT, then clearly that data can flow outside and then we don't have any control anymore. So how do we protect that information as well during the inference phase? And then finally, scaling limits. So we know, except very few large companies, access to compute, access to data is a big problem. And if we really want innovation to happen at the edges and by developers at a small scale, then we really need to create this crowdsourcing of compute and data. And we'll be hearing some of these tools from some experts in our panel as well as keynote speaker. And with that, I will let you speak, Rohan, and introduce our speakers.
Great, thank you. So we had some more people come in. I just want to share this one more time. The Luma calendar to say updated with all of our events and our WhatsApp channel. So make sure you join these. And with that, I'll be resuming. Okay, our first speaker is Martin Yagi, associate professor at EPFL. I'll be passing the mic to you.
Cool. Thank you so much for organizing this and for the opportunity to speak here. So let me try to share. So does that work with slides? Very good. So yeah, I'll keep this short. So we'd just like to discuss some aspects of decentralized training and then touch on how this addresses large language models in various ways, right? I mean, for example, in my group as well, we've been working a long time on decentralized training of traditional machine learning models, and now it's kind of interesting to revisit all these questions again in the world of LLMs, and then I'll finish by mentioning software aspects a little bit. So the setup, I guess, is pretty clear and standard. So we just have a distributed data set over several agents, and we're trying to collaboratively learn. So what does learning mean? In the simplest setting, learning would mean that we want to fit the entire data set, which you could see on the top right, for example, to learn from the union of all data without moving this data around, right? And the data can be stored in, for example, hospitals or different countries or so, which speak different languages, or individual devices as well, where, so depending on the setting, you might have vastly different numbers of participating agents. So just as a very high level overview, I mean, there's been a trend a bit to move from the centralized setting, as was already mentioned in the introduction, to a more decentralized setting where we do not share the data, and there's so many settings where this is just unavoidable, right? That sometimes even by law it's just not allowed to bring health data out of a country, for example. So there's very good reasons why we want the data to remain where it is, which means on the agent that's participating in the setting. So now how can we collaborate? And there will be some subtle differences, which I'll try to get into a bit, between federated setting and the decentralized setting, but this would be rather nuances, but I think it's clear that this is the way we want to go. So in the federated setting, we have again the whole union of agents, and we just trying to fit everyone with the same model. So here X is the model we're trying to learn, and we are just trying to make this model fit for everyone, and that means we just sum up everyone's loss. So that's what the federated learning would do. I want to generalize this a little bit, or do this twist to it, which means that we want to allow people to have different models, and we want to, so in other words, have everyone have their own learning task, right? Everyone can learn a different thing, have a different goal, and these are the different losses or task functions here, which everyone wants to minimize. Now the main difference now is that now everyone has a different model. So this is called personalized learning, and that's, I think, getting more and more important, especially in the world of LLMs as well, because we see that LLMs can be fine-tuned for many tasks very efficiently. But the question now is if this can also be done in a collaborative way, right? So of course everyone can fine-tune alone. That's always a baseline. Everyone can train alone. That's always what we need to compare to and what we're trying to beat. But the goal is to be better than that. So is that possible? And I mean, in traditional ML, the answer is pretty clear. But what we tried in this paper here is to give a better answer also for the LLM case. And there's kind of two main aspects here I like to mention. And the first is the kind of heterogeneity of data you have, right? That is just, it's just very different now that we talk about the text and LLM. So in this paper, we wanted to study this and try to see what happens if you have a realistic heterogeneity between the training data on each agent in terms of text. For example, here it was different languages in Wikipedia, different categories of news, for example, and different programming languages, and every agent only had like one or two of these specific categories. And the question is, can they still benefit each other, right? Can you do better than fine-tuning on your own data alone? And the answer is yes, but you cannot do it with standard federated learning. You need a collaborative selection mechanism. What that means is you actively need to work on identifying who is useful for you for your optimization task, right? And these are probably the agents which are more similar to you, but what do we mean by similar, right? So the approach here is a decentralized learning method that everyone trains their own model, and while they train, they exchange information. I mean, what do I mean by exchange updates or information? In this case, this would be the model updates. And for example, we can compare our models on predictions on, for example, on a public data set, or also on everyone's individual validation data set. And we can use that information to decide, do we want to collaborate with this person or not? And I think this is an important setting because we have very heterogeneous data. We also have low quality data sometimes in realistic setting, I would say. So how do we identify this data and make sure the training still succeeds and is still better than training alone? So we use pretty simple standard techniques like LoRa adapters, which make you work and share only a much smaller amount of parameters compared to the full LLM. And last but not least, I'd like to mention that it's maybe also a good step towards a kind of a compensation mechanism, right? It's not that yet, but these weights that we get on how useful one agent is for another agent, that might be a nice quantity to study if that quantity could also be used to maybe in the future reimburse these people, because this quantity, which you by the way see on the top right, how much an agent helps another agent, that quantity could maybe be used as an incentive mechanism, though there's a lot of open work to do there, right? If this is symmetric, if this can be gamed or not. But I think it was interesting to kind of revisit this question for the LLM case. And that's actually the main thing I wanted to talk about. But I want to say that there's also more aspects that now come up again, which sometimes are already studied for traditional ML, which now should again be revisited for the LLM case. And this one here is extremely close to what I was just saying, like who do we collaborate with? That also includes the the case of having malicious agents, right? Or having, this is also called data poisoning, basically. Like if someone in the collaboration is actively putting data that's maliciously drafted to poison everyone else's model, right? So how do you avoid that? And I think it's really cool that the same kind of mechanisms that used for collaborator selection, which is like making sure the updates you get are not too far from your own updates, these type of mechanisms, such as this kind of clipping, can also give you provable results here, that you can actually give training guarantees that you're not affected by these workers, which is called Byzantine robustness in terms of robust training. So, and it would be cool to do more on LLMs with this type of techniques. Last but not least, the communication aspect would be nice to revisit some more. So for the moment, we just exchanged low rank adapter updates, which are of course smaller than the whole model, so that helps. But there's more to do. I think we often have kind of interesting low rank structure in gradients of LLMs, so this can be explored more. And there is also techniques that work with this in the decentralized setting, when, I mean, in the peer-to-peer setting, when everyone has a different model and shares their updates with their neighbors only. So this is some older work we had in the distributed setting in a data center, but now in the decentralized setting for LLMs on slower, more distributed devices becomes more interesting, right? Because the models became larger and the communication bottleneck becomes bigger now that we have LLMs. So that's almost it. Of a bit. Two more slides. Like one is that we also worked on medical LLMs. So this is just want to mention it because it was a nice case in the sense that we could also open source the data set that we use. So we have kind of a good baseline now, what medical LLMs can do. And now then we can try to get this attribution again, like where do capabilities come from? What was in the training data? What kind of aspect of the training data was how important, where do the biases come from? I think for this is very important to look very carefully into the data. And for that, we need to have transparency on the data. And even if you talk about the decentralized learning, right, that's exactly why we like decentralized learning, right? Because it allows us to be very careful on getting more data, and it allows us to access more data, to give the decision to participate on back to the data holders, which can be super interesting here, right? If you, for example, talk about different countries which have different medical guidelines, so how do they collaborate with each other to still learn from the medical practice of another country, for example, which has other guidelines, which uses other languages and so on. So this is a very interesting topic, and we haven't done much on decentralized yet in this setting, but it would be nice future research as well. So last slide, software. So this might be a bit surprising because this is a JavaScript here. That's something that we are quite interested and passionate about because it's like super low entry. Everyone can use it on their phone and in their browser. So, I mean, this is not what we did in the paper I showed you, but this is something that I think is promising, and we're looking for more collaborators. And I think it's cool that we see other initiatives as well to bring LLMs to the browser. And the next thing is to also bring fine-tuning to the browser, that people can just connect their own personal data without that leaving their device, and participate in this such collaborative training, and use algorithms like I described. So I think this is a cool direction, but a lot of work remains to be done because the efficiency is still a bit behind the Python world, but this gap is closing quickly. So very interested to get your views, and please join us on the GitHub. And I would say that's it from my side. Thank you very much.
Super cool. This is a lot of interesting stuff. Even though I've been following your work, got to see some new interesting things. So we are taking questions on Zoom, and also we'll take questions in the room. But just to get started, so I had a question on collaborator selection. So I'm curious to hear your thoughts on like in which kind of problem settings you're seeing collaborator selection could be more important or like has better performance than, let's say, a baseline, which is more like a random selection?
Yeah, that's cool. I think it really depends a lot on the data set here, and that's why I think it's so cool to now revisit this for LLMs, because we have much more interesting kind of data heterogeneities. So yeah, what we tried, of course, was these different languages and so on, but I think much more should be done, and it would be very cool to explore more, right? It's also interesting because LLMs are kind of general purpose agents, right? And then on top of that, the fine tuning kind of only adds a specialized ability. So I like the question on which abilities actually are beneficial for each other in the sense that, yeah, they benefit from the collaborative fine tuning, and yeah, it'd be good to see more. And thanks to decentralized learning, we have an opportunity to maybe access more data sets which would be not accessible in a centralized way. And yeah, that did not answer your question, but it's a great open question.
Makes sense. Also, on these LLMs specifically, is it a benefit if you are personalizing models on device and also with collaborator selection that you can get away with a smaller model size instead of having to go through, let's say, a centralized very big model, which is performing amazing for everyone, but if you're only interested in getting good performance on your data, which is personalized learning use case, do you see model size can be reduced much more?
Yeah, we haven't tried this, but I mean, given the results, I think the answer should be yes, because you get better accuracy than if you train alone, right? So yeah, you could reduce a bit of the model size. Yeah, maybe the other answer would be that because of the low rank adapters, in a sense, you do have a smaller model than the big one, or at least you do have only a smaller part that you are modifying compared to the big model. But also, yeah, other ways how big models can collaborate with small models is also a cool research question. So the method I showed here is maybe not giving you that, because you're exchanging gradients, so the model needs to be the same. But if you want to learn between different model sizes, you can also use the predictions like distillation based. So based on everyone else's answers, you can update your model. So you're not restricted to have the same size. So I think that might also be promising. Yeah. So.
Okay, there's a question here. Go ahead.
Are you able to hear? Is he able to hear?
Can you hear, Martin?
Yeah.
Okay, great. You had mentioned that in terms of being able to figure out who to collaborate with, you'd want to compare how similar the results of a different model are to like the baseline or the gold standard. If I understood that correctly.
Yeah, that's right.
So my colleague and I work in women's health, and one of the things is that women were not included in clinical trials in the US till 93. And we often say in data science, GIGO, garbage in, garbage out. So our baseline is garbage. And if we start to surface information from multiple sources, like we may get a very different result because we have very different data. So in that scenario, what would your recommendation be about how to assess what to believe if we know that our gold standard is garbage? We don't know that we're getting, significantly better or significantly worse if it's very different.
Yeah, that's a very important topic. And so I guess the two parts of it, like one is on the training side, how can we make sure everyone is included in that and represented? And then the other question on the evaluation side, how to make sure we're evaluating the right thing, and that is super hard for the LLM case. And also maybe there I'd like to mention one initiative we are starting with Marian Hartley from the Yale University and EPFL as well, on some global evaluation benchmark for medical LLMs, where you would really have medical doctors from each country, also in low resource context countries, and from all populations be represented in the evaluation to make sure that the evaluation can be trusted, right? And then on the training side, you're right. I mean, the training data was extremely biased, so we need to make sure we have more inclusive and more representative training data. But for that, I think the decentralized learning paradigm is an excellent avenue to go, right? Because we have decentralized learning, that might actually be the chance to actually include these communities that you mentioned, which were now not included, right? Due to the centralized nature of the approach. So if they actually have the option to be included by giving them the power to decide to join or not this training, I think that would be a better possibility to actually do include them. But yeah, it's I think I'm hopeful that decentralized learning can improve it, but of course it's not a silver bullet. I think the social aspect is very difficult, how to incentivize all these communities to actually do take part in this, right? So
Thank you.
Any other question in the room? Also, people who are on the Zoom can ask questions in the Q&A and then we'll surface it up. Oh,
Is
go ahead.
this, I have a question here. Is this new approach of decentralized artificial intelligence applies only for the training phase of the machine learning algorithm, or also for the inference phase? I mean, when you have the model already deployed in a real production environment, will we use this kind of decentralized architecture or only for the training phase?
yeah, that's right. In our setting, it was only for the training case and the fine-tuning case. We have not studied the decentralized inference, because that you would only need if the model does not fit onto one agent anymore. Only then you might need decentralized inference. But then, of course, you might do it for different reasons, like for resource sharing perspective, but that would be a different scope here. So here's we need to keep the training data where it is while still enable training or fine-tuning.
There is one more question. Go ahead.
Yeah, great talk. I wanted to make a comment about collaborator selection via prediction agreement. It's a slightly philosophical point. I'm working at the U.S. Naval Research Laboratory in the summer on the logic of AI safety. And so disagreements are actually the main source that we have for knowing how wrong we are. It's not agreements. If we all agree on the room, we could all be wrong, right? And we wouldn't know it. But if two of us disagree, we know that at least one of us is not 100% correct, right? If not both of us. And so when it comes to decentralized AI, I would encourage people to actually look to have disagreeing models to be safer, right? Because if you're making error-independent models, that's what you want, right? To combine things. Correlated models that are agreeing with each other are useless.
Yeah, I love this comment. So you completely on the same page. Like I skipped a bit over this, right? I mean, we have several different strategies on how to do the selection. There's like 3 strategies, for example. And the prediction agreement here, you would ask, agree on what, right? And yeah, if you start to just agree on a public set of questions, then it's very dangerous, as you mentioned, because that might be circumvented and so on. One thing we also tried here is that everyone can have a secret set of questions that they have and not give that out. So that's the stuff that you trust for your task. And then you receive models from your collaborators, and you can test those on your secret data, secret questions, and see if they agree with you on your secret question. So then it's maybe a bit more safe to do. But yeah, I have to say the goal here was not on safety yet, but just on the training speed, right? But yeah, if safety is your goal, then you need to be much more careful on this. But I think it can be done. And this is another aspect also with the Byzantine learning. If that's part of your threat model, that you have arbitrary updates from everyone, then also something.
And to quickly jump in, actually, we have a paper with Professor Yagi where we show this phenomenon of collaborator collapse, where if you find and only collaborate with very, very similar collaborators, which is basically prediction agreement or similar weights, then what eventually happens is these small set of models collapse in a very small region where they're only collaborating with each other, but not collaborating with this dissimilar, but still useful models. So I think this area will probably show lots of interesting dimensions. Okay, I think we're running out of time. So we will take the questions from Q&A probably later. Thank you so much, Professor Yagi. And
Thanks so
let's
much. I'll stop
okay.
sharing this.
Okay, Rohan, okay, perfect.
Great, thank you so much. Our next speaker is Holger Roth, Principal Federated Learning Scientist from NVIDIA. If you'd like to take the floor.
Yeah, hello, thanks for the introduction. Yeah, and thanks for inviting me here. Let me start with my slide deck. Okay, you should see the full screen, right? Yeah, so I'm gonna talk more on the tools side of things for enabling federated learning in real world deployment. And at NVIDIA, we've been building this open source platform called NVIDIA Flare, which I would like to introduce here. So our motivations, of course, are very similar to what we already heard from Professor Yagi. Also, maybe one use case to mention in the what we focus on is this cross-enterprise scenario where you might have different companies or different hospitals with a lot of data collaborating, mostly because of the compliance issues, right? Regulatory constraints. But there are also practical reasons, like sometimes the data is just too large to physically move or centralize anymore. We have use cases of autonomous driving where you're looking at data sets on a nation scale, right? Just copying these across data centers will be infeasible. So it becomes as a federated learning or decentralized AI becomes a tool that is really relevant for the scalability of AI. And of course, it is a core technology for enabling privacy preserving machine learning, right? So we have multiple layers of security built into NVIDIA Flare, like homomorphic encryption, differential privacy, and confidential computing. The whole open source toolkit is published under Apache 2 license, so it can be used in commercial applications, and is also hopefully useful for researchers. But there's really a focus on the production readiness, right? So we enable different cross-internet communication patterns. We have tools for scalability in the production setting, like high availability. What is if your server fails, you can automatically transfer to another server. You can run multiple experiments in deployment and the same in parallel, same time, right? We have tools for converting your centralized training code to a federated learning setting with a few lines of code changes. We have actually done quite a bit of work to enable streaming of large models. So if you want to do fine-tuning of large language models, which could be tens or even hundreds of gigabytes of data just to share the model parameters, right, across sites, you need to have a reliable communication that can have a lossless communication across the sites. So that's available in the latest release. Overall, it's a framework and model agnostic implementation. So you can go from PyTorch, TensorFlow, different model architectures from deep learning to classical machine learning algorithms. And yeah, some of the privacy preserving technologies that we have built in and also support with the latest confidential computing hardware on GPU with the latest Hopper architecture. I think I mentioned this already, but we have different communication patterns. Like you can set it up as a server-centric setup or peer-to-peer communication. There we can do federated averaging, split learning, swarm learning, etc. And everything is layered and pluggable. Okay, yeah, so please take a look. Here are some like of the major use cases for image segmentation, large language modeling, XGBoost to show one of the more classical algorithms as well. And on a high level, the architecture is really a distributed computing framework, right? So reliable communication across the internet, matching or coupled with the distributed computing. So you set up a controller on the server side that can basically act as an orchestrator of your workflow. The controller can assign tasks to either all clients or a subset of the clients. And the clients are running executors, which can listen to certain tasks. So once they receive a task that they can execute, which might be a local model training, right? Take this current model, these current model parameters and fine-tune them on your local data. They can do this and send the result back to the server. The server could then collect a set of model updates from the different clients and aggregate them to do a global model update. So in this way, you can imagine that you can easily implement a federated averaging algorithm. And as indicated here by this filter, like at each point of the communication, we can insert so-called filters, which can do things like adding encryption, adding additional noise for differential privacy, do some kind of sanity checking, maybe on the client. It's more, I would say mostly on the client side, you're concerned about leaking data to the server, right? So you might want to do some checks to quantify the amount of data leakage or add additional privacy preserving techniques. Or you could even also do things like detecting a malicious code or malicious model weights, right? So these filters can actually be enforced by the data owners. So there are these local privacy policies that are guaranteed to be executed. So researchers who are submitting code for experimentation cannot override these kind of privacy measurements. So yeah, so there are several layers of security and privacy related measures that are implemented in NVIDIA Flare to enable this real-world deployment, coming from the user identity verification, data encryption, the security policies I talked about, and then the additional privacy preserving algorithms, also including confidential compute on as a hardware solution. And that all makes NVIDIA Flare domain agnostic, right? We can apply it, and we have use cases across different industries, starting from healthcare, finance, autonomous driving, biopharma, and so on. There's a list of institutions and companies who have used it in real-world deployment of federated learning and for research, with a growing list. And we do have in the repo also several research examples that mostly came out of our team, but we also have some collaborators who contributed some examples. One interesting work is on automated machine learning, right? So now in the federated learning, you have actually more, you can imagine that each client is doing their own model training, right, on their local data. So they have potentially their own hyperparameters that can be tuned. And actually it shows that if you find the correct combination of the optimal combination of hyperparameters across the different clients, you can achieve quite a boost in performance. So the idea of automated machine learning is that you can use some tricks like reinforcement learning to find the best parameters for your data set and training scenario. Then I also mentioned that this concern that by sending model updates to a central server, you might be still leaking information about your private data. You can actually do some quantification of how much that leakage is, depending on some training parameters, like what is the batch size, how large is your local data set, and things like that. So we did some work on gradient inversion to quantify how much can be recovered with like a state-of-the-art reconstruction attack. And this, I think, is also an interesting topic. Is like how can you quantify how much each client's data set is contributing to the overall model performance. So this contribution estimation becomes really relevant. And we've done some work on personalization. So a combination with what we call a supermodel, SM here, is basically fine-tuning different variations of the model depending on the local data set distributions. Okay, so I just want to end here with a couple of things that might be interesting. One thing is we have the NVIDIA Flare Day coming up next month on September 18th. So that's like the first year we are organizing this, and you will see a lot of real-world users providing their experiences with deploying federated learning, both research and real-world applications. A lot of them come from industry. So we have a full packed event with several speakers. There's the GitHub and the website to learn more about it. And one thing to keep an eye out for is this NVIDIA academic grant. That is, I think the call for proposals will come later this fall. And there's like a topic of edge computing and decentralized AI. So you can probably put in some proposals there for getting support from NVIDIA. Okay, so thanks for the attention. And if you have any questions, please reach out to me, or I'm happy to answer them here.
Thank you so much for the talk. Once again, we are going to take questions on the Zoom in the Q&A section, but also in the room. If you have any questions, feel free to raise a hand. I'll get started first. So I have a question on the federated learning for healthcare use cases. I'm curious to hear more insights on how like these institutions are actually deploying these systems, and are they using it for like biomedical imaging or some clinical text LLM? Like what kind of use cases or any other insights you can share?
So historically, our efforts came out of the medical imaging sector. So we've done a couple of studies around mammography, breast density analysis. We did a COVID study which looked at chest X-ray and some EHR features. So that was already like a multimodal model that you would deploy on the different sites, trying to estimate a need for oxygen treatment when patients with symptoms of COVID arrive at an emergency department. Yeah, there are big efforts in brain tumor segmentation. There's a federated brain tumor segmentation challenge that has been going on for a couple of years. Yeah, so medical imaging has been a big sector, basically because of these patient privacy concerns and regulation. Like in healthcare, it's very difficult to share data sets. So I think there has been a lot of motivation from different teams in healthcare to do federated learning. But I don't think there's any limitation on being just imaging, right? Like multimodal models, vision language models are becoming more and more widespread. So people are, of course, applying those to federated learning. In our experience, we mostly looked at these, as I said, the cross-enterprise or cross-silo use case, right? Where you have these maybe individual hospitals, they have relatively large databases and compute resources that connect with a central server to do this collaborative training of an AI model, mainly towards improving the generalizability. That's what we showed in all of the studies, was basically by having these more diverse training data sets across different patient populations and scanner devices, you get much more robust models compared to AI models that any individual hospital could have trained, right? But I think there are a lot of use cases also for this cross-device scenario. Yeah, if you think about like wearable devices, like measuring heart function at patients at home and things like that, right? Like it's maybe technically a little bit more difficult to implement because of compute resource limitations and things like that. But I think there's a big use case there also to be explored for wearable devices or like on-scanner devices. We have, of course, some CT scanners and MRI. They nowadays have GPUs installed for the image reconstruction, right? So you can actually do some on-device training there as well. And for the surgical room, for example, we have NVIDIA HoloScan, which is like a small scale compute device based on the Jetson architecture that you can use to do things like deploying AI models for surgical videos analysis. And they're actively looking into deploying federated learning approaches for monitoring and updating some models.
Perfect. That sounds like a lot of use cases.
Yeah.
Is there a question here? Or anyone in the chat? I think there were some questions before. So one question, I'm going in the reverse order, is what strategies does NVIDIA Flare use to optimize communication efficiency in FL, especially when dealing with large models or limited bandwidth?
So for the large model support, we implement a streaming approach. So you basically chop up the model parameters into small chunks and then stream them individually. We tried gRPC has some limitations. If you use it on the single message size, I think it's 2 GB, which a lot of these large language models are exceeding. And some of the streaming support that was built into gRPC wasn't reliable in our experience. So we actually do the splitting, this chunking of the data ourselves, and then basically build in some robustness, like some automated retries if any of the communication fails on the individual chunk level. So in that way, you can basically ensure that the whole model message is being streamed. It might take a long time, but you can get the full message. Of course, there's going to be we have some like built-in compression. That's I think it's already built into gRPC. So that's being used, but I think there's you can probably do things like pruning and finding like the most relevant parameter updates in the large language model to send to communicate would probably help a lot. We haven't really explored it much at the moment, but I think it makes a lot of sense to look into that. For now, we basically like assuming you have the resources and the bandwidth to do large language model training in a federated scenario, you can do it with NVIDIA Flare.
I'm curious, so following up on that question, do you think there are some model-specific optimization you could do in terms of communication?
I mean, one thing, of course, that we have also examples is the parameter efficient fine-tuning, right? So if you do low rank adaptation, then you would have a much smaller set of parameters that are being trained, right? So your message size is already reduced. I think the example that I looked at personally is doing lower, or like we even looked at some prompt learning approaches, right? You can do the p-tuning and things like that, where you really just learn some additional tokens that are being appended to your model input. And that helps you to condition the large language model to do like a downstream task. And really just builds on the strengths of the large language models that are so generalizable, right? They have a good zero-shot capability. So with relatively small amounts of adaptation, you can already get them to do what you want, and the communication cost is very drastically reduced if you do that.
Yeah, makes sense, especially in the context of low rank adaptation. Any question in the audience? Okay, one more question is around, can you share if NVIDIA Flare supports federated analytics and not just learning?
Yeah. As when I showed you this high-level architecture, right, which I can quickly bring up here. It's really just distributed computing, right? This controller can implement it any kind of task, right? If you say like the task is send me your data statistics, you can send it over. We don't like the platform itself doesn't enforce any privacy constraints, so you could even send out data, right? So it's up to the user to apply the correct filtering and things like that. Of course, we have like the examples that are good practices, so people can enforce containerized environments where people cannot change the code, and then running it in a confidential compute environment, you really reduce your attack surface for any potential manipulation of the code. But as a framework, there's really no limit on the flexibility as to what kind of tasks you can assign and execute.
Awesome, thank you. So we are running out of time, so we'll take more questions later. And for now, let's thank the speaker again and look to the final session.
Thank you.
All right, Rohan, please take it away.
Great, thank you. Next up, we have our panel. So let me introduce the panelists. Vincent Weiser from Prime Intellect and Ben Fielding with Jensen. Vincent, if you'd like to take the floor. Or Ben, you're on, so let's go with that.
Hi. How much time do I have for the presentation, and then, should we present briefly in the beginning and then jump into the panel?
Yeah, that's the plan. So if you can quickly present for between 5 to 10 minutes about what you're building, and then we'll do more Q&A.
Perfect. Do you want to go ahead, Ben, or shall I?
I'm easy. Yeah, I'm speaking. I can jump in. So I don't have slides to share, but I can just kind of run through a bit of a kind of explanation of what Jensen is and some of the beliefs that we have about specifically decentralized and highly distributed machine learning and how it's going to progress. So at the very top level, Jensen is a machine learning compute protocol. So we're a base infrastructure layer to allow machine learning training work to be done on any device in the world. The idea is that when you're training a machine learning model right now, you typically use either local hardware, so you'll have a workstation with a bunch of GPUs in it, or you have access to a cluster of some kind, like an HPC cluster or something, or you rent from a data center, like a hyperscaler data center or something. So you're going to AWS or Google Cloud or Lambda or one of the kind of long tail of GPU providers, and you're directly accessing the hardware that they have. Jensen's view is that the future can be more of a kind of distributed fog computing platform where theoretically you can access any compute device in the world if the owner of that device is willing to rent you access to the device. We've seen this be successful in the volunteer compute setting with things like Boink, SETI at home, Folding at home, the kind of list of these large-scale volunteer compute systems that allowed distributed computation to be spread about over people's home devices and people's spare data center cycles. Making this an economically kind of viable alternative introduces a bunch of challenges, though. So if you kind of wrap some kind of monetization mechanism over a volunteer compute network like that, or even a kind of small incentive like a leaderboard, you introduce the incentive for people to lie about what they're actually doing. There was a kind of funny example of this where I think it was Boink. I can't remember which one of them. One of those volunteer compute networks put in just a top 10 providers leaderboard. And it was just to try and recognize the people that were providing compute and say, hey, look, we sort of celebrate you. that very quickly got gamed, and the top people on that leaderboard were people with ludicrous kind of amounts of time supplied because they were just gaming the mechanism used to calculate it in order to be the top person on the leaderboard. So as soon as there was any kind of micro incentive, people gamed it. And so we look at that and we say, okay, we'd like the idea that somebody could come along and pay to use this network, but people will definitely game the payments. So what do we do? And what you need to do there is introduce a verification system where you can check the work performed by the compute providers. Implementing a verification system means you need to implement some level of trust. Implementing some level of trust means you probably need a trusted entity in the middle that checks everybody, verifies they are who they say they are, and they've done the work that they say they do. The problem with that is that doesn't scale. If you have an entity like a company doing that, the administrative cost of doing that becomes absolutely ludicrous. But you can do it in a decentralized way if you have some way of making decisions over the group of participants that are providing their compute. And so we took this idea 4 years ago and said, okay, well, blockchain provides us with a way of doing decentralized decision making. We can have consensus-based decisions over a group of people without one kind of having power over all of the others. That's an incredible technology, but how do we then build a machine learning compute network over it? And for the past 4 years, that's what Jensen's been doing. It's been solving those research problems, essentially. And so out of the end of that now, we have the kind of seeds of a base foundational layer for machine learning work to be performed on any device in the world. It involves generally 4 kind of technical areas. One is communication and coordination. So the bit that I mentioned about collective decision making, how do you get people to just connect up to some kind of peer-to-peer gossip network and agree on decisions that they're all making together? We have a blockchain system for that we're building. It's a standalone layer 1, and it focuses purely on making kind of machine learning task-based decisions together as a group. It also focuses on achieving a system for distributed data availability that's attested to by all of the participants, i.e., if I have a really big piece of information, how can I agree with everybody kind of in the room here that data is available to a new participant? Well, we can build a system for that using commitments and kind of erasure coding and things around that specific piece of data, spreading it over the participants in a RAID style. So we do that. The next big portion of work you need to perform is serialization and execution of machine learning tasks. So if I have a PyTorch model, how do I actually serialize that into a format I can send to any one of you if you're part of our big kind of distributed network? How do you deserialize it, know that it's the same as the model that I sent you, and then how do you execute it on your hardware? And so we have a new compiler stack for machine learning that takes high-level defined machine learning models and distills them all the way down to specific pieces of hardware in a fully reproducible and deterministic way, so that I know that if I send you my model that I've written in PyTorch or JAX or TensorFlow, you're going to execute it in a defined way on an NVIDIA piece of hardware or an Intel or a kind of Mac metal hardware or any kind of number of these different pieces of hardware. That's a really hard thing to do, and it's an iterative process. But we have that working for NVIDIA hardware right now, and we'll be kind of expanding out to other pieces of hardware as we go. There's an interesting piece there that this is one of the only places, or this is one of the only situations where there's a true incentive to build an actually open machine learning compiler. If a company kind of goes to build a machine learning compiler, typically they have to keep a lot of it closed source in order to have a business model. Whereas the business model of having a big decentralized network for compute provides an incentive for us to completely open source that compiler stack and kind of gift it to the world, as it were, which is what we'll be doing. This has really interesting downstream effects on reproducibility of research, where right now, if you want to send somebody a model and them execute it identically to how you did, they're going to have exactly the same hardware as you, otherwise it's not going to work. This compiler system would mean that they could do it over different pieces of hardware and get bitwise reproducible results to you, which should be a big kind of gain for the research community. Next up on the 4, verifiable computation. So how do you take those models specified in the execution framework and check that they were performed correctly now that you can agree between all the participants on kind of small things, how do you take a massive machine learning model and agree on that execution? And so we have a system of proofs, basically, where you take portions of the machine learning model training, you do it deterministically, and you selectively rerun portions of that training job. We also have a cryptographic proof where you can do a training or inference run, and you can distill that run down into a set of cryptographic commitments, which can be checked much more easily than rerunning the task. This is in the same genre of zero-knowledge proofs and snarks that you see in the cryptocurrency world, but we apply it purely to machine learning operations, so matrix multiplications, essentially. Its pure purpose is to verify matrix multiplications. It doesn't do anything else, but it allows you to take a large-scale machine learning job and agree that it was done correctly without doing enormous amounts of extra work. The overhead is something like 10 to 30% rather than kind of 600 or 700%, which is what it is in the general purpose world on something like Ethereum. Finally, we've got distributed efficiency, which is the kind of last big problem that most machine learning familiar people will point to, which is if you are to connect up all the world's machine learning capable compute, is that network actually going to be useful because of the latency and bandwidth constraints that you'll see on a network like that? If I'm going over consumer bandwidth, consumer broadband, or I'm going between data centers, is it going to be efficient enough to build a model over this? There's kind of two answers to that. One is you can treat this as one big optimization problem, and you can efficiently shard and schedule over those devices. And so we do research in that arena, and we'll have a paper coming out early next year, which shows an efficient way of doing that using existing models. The second piece is how do you build models uniquely designed for an infrastructure like this? That's where it gets really exciting, but it's very long term. And so you say, okay, right now we build models over 4,000 GPUs in a data center, say, because that's the most we can connect up in with hyperfast interconnects. But what if we had millions of devices that had slower interconnects? Would we build models in a different way? The answer is yes. We'd probably build along the mixture of experts lines, but expand it out much, much, much further, where you maybe learn the communication styles between the different chunks of kind of model that you have over that network. And we do research in this arena as well. We'd love to collaborate with people on this. We think it's a pretty heavily unexplored area. But the easiest way to think about it from the Jensen perspective is if you were to build a graph of all of the machine learning capable compute in the world, you would have this kind of weird semi-sparse graph where there'd be really dense pieces, which are the data centers like the hyperscalers have. So Meta's data centers would be heavily interconnected, dense pieces on this graph. And then you'd have really sparse bits, which are all of the kind of workstations that exist, the small academic kind of builds, the small data centers with smaller startups, etc. We would like to just connect to that graph so that you're now able to access all of those disparate pieces. The optimization process of building a model over that is then a problem for the world rather than being a problem for the kind of connector of the graph. So in many ways, we want to solve this problem ourselves, but we also want to just create the infrastructure so other people can go out and solve that problem. And we'd love to see researchers now able to access much more compute and able to build kind of weird and wonderful models over that infrastructure, rather than the current state of the world where researchers sort of have to scrap about looking for access to an HPC here or credits on a kind of data center system over here. We'd like them just to have this free market where they can scale out over the compute, but they now have this problem of latency and bandwidth to deal with. I'll stop there. That was a longer than intended explanation, but they're the kind of four main areas of Jensen. Please check out our website, jensen.ai, if you have any kind of other questions or want to read more about how we do what we do. And if there's any interest in collaboration, obviously, please reach out as well.
That's a very exciting summary, and I'm sure people have lots of questions, at least I have. But before we go there, we'll first go to Vincent. And
awesome. Give me one second. Sorry, I have to rejoin to screen share.
Okay. So I'll have to, I guess, Rohan, you can add him in case he joins as attendee as a panelist. Rohan, can you hear me? Probably not.
Yep.
No, So while Vincent is away, a few questions for Ben. So can you talk more about the incentives aspect, like what kind of incentive system you're creating so that people would like to contribute their resources and join this network?
Yeah, really good question. We feel quite strongly about this. So the underlying incentive in Jensen, the idea is it's pure kind of market. So if you are providing compute, you should be paid for the operations that you perform. And if you're using this network, you should pay for operations to be performed. So we think the current market for machine learning compute abstracts away the real thing that's being transacted, which is just floating point operations. Ultimately, it's kind of matrix multiplications. It abstracts that away with the kind of best devices and the new label like A100 or H100 or something like that. But realistically, what most users care about is how much they're paying for their ops, and then kind of downstream the efficiency of those ops. And we try to move much closer to that situation. So we want the incentive in Jensen to be pure kind of transaction between somebody who wants to perform ops and somebody who wants to have ops performed. There should just be a basic trade between those people. In order to get there, you can incentivize other things. So you can put in the proxy incentives, you can put in kind of additional rewards for providing compute because it's a marketplace. Sometimes you do want to bootstrap one side, but you need to be incredibly careful with that bootstrapping because it distracts from the actual purpose, which is just to have this marketplace. And so our kind of strong belief is build the marketplace. If the marketplace has value in the world, i.e. if there are people on either side, then that value will be realized. Rather than kind of falling too deep into the trap of trying to reward people for doing something and then those rewards being gamed. That goes back to that example of the leaderboards, where as soon as you put any kind of reward incentive in front of people, we assume, not maliciously, just people are kind of financially rational, they will game that in order to get the best reward. That's just how people operate. So there's a lot of game theory underneath it, where just designing that kind of incentive structure is quite difficult. And we think it's one of the issues with the kind of crypto Web3 blockchain space is that it falls too heavily on the side of creating incentives, in our view, and not heavily enough on the side of creating something that parties just want to interact with and are willing to pay for. So yeah, that's our view on incentives. Create a real actual market where two sides want to interact and transact. Don't create kind of a one-sided incentive sort of game, because it will get exploited.
Awesome. Let's have Vincent now as our
Perfect.
speaker. Yeah.
Yes, I'll keep it concise, and also building on what Ben shared. Like we are also kind of like collaborating closely on leveraging some of the things that Jensen is building, and basically for like what we're doing with Prime Intellect, what the broader goals is really kind of like building decentralized AGI and making it accessible to everyone to advance science. And really the way we do this is kind of like by aggregating all the compute out there, including different data centers, including someone like Jensen down the line, including the centralized clouds, but also including the decentralized clouds, and making it possible to train on them through distributed training. And then kind of like going back to Ben's point, creating markets not only for compute, but also for intelligence. So basically creating a two-sided market where people can incentivize AGI and intelligence and on different dimensions, and then basically having people to build these AI models and get rewarded. And I think maybe more broadly, like this view is also informed a bit by this like different scenarios of how like obviously the next like decades of AI progress could go. Obviously here to the right is kind of like the extreme case of like that it's possible that we go to like AGI and super intelligence even in the next decade ahead, which I think to an extent with AI labs is the base assumption, you know, from DeepMind to OpenAI and others. There's this good long read up on this from Leopold Aschenbrenner called Situation Awareness, which I can recommend for those that haven't read it yet. But this kind of also informs our view that we want to create kind of like a multipolar world that isn't kind of like this unipolar outcome of like the like CCP China or like a nationalization of AGI or ASI, which I think is incredibly dangerous actually for like global order and freedom. So that's kind of like the broader motivation, and really like I think how we will get there, which is also on this graphic, is really on this point towards like automated AI research and automated science is basically I think really when this starts to move more fast. And kind of like how we built this is really by building a protocol that incentivizes compute but also intelligence, and kind of like a broader obviously community that can build and fund these decentralized AI models. And then the first step, what's already live and used by many AI startups and developers, is basically like a big compute platform. So we have like tens of thousands of H100s and like different platforms on our system. And also like stuff like, for example, being able to use multi-node on demand, which almost no other cloud has, is basically being able to use a large amount of compute instantaneously for as long as you want. And really the piece that on the research side that I want to share briefly on is on the decentralized training side, where we did like a lot of work. So basically, to motivate also decentralized training, the goal really is to train globally across different data centers and be able to like harness and utilize underutilized compute. So one way to visualize this is that you have obviously like tens of thousands of different like data centers and locations, and even the really big guys like Google and OpenAI are not able at this point to fit all the GPUs for their frontier training runs into one location. So for example, Gemini, like Google's frontier model, has been trained across different locations in a distributed, like slightly distributed fashion. And obviously there's like the challenge or like the goal really is that one can fully leverage the underutilized compute. So if there's some cheap compute in some specific locality or data center, that one can train across it and in a quite dynamic way. And obviously the key challenge there is distributed communication, as well as some others. That basically you need to communicate between all of those data centers instead of having one centralized cluster. So yeah, like slow interconnect is one of the technical challenge. Then obviously there's even like non-homogeneous hardwares that you might have A100s, H100s, AMD chips, Intel chips, other chips available. And obviously it's difficult to train across them. So that's also one challenge that we're working on resolving. And then kind of like this on and off ramping of compute, that you might have like compute, like very cheap compute open up in the middle of your training run, and you might want to leverage that, which is like another technical challenge. And then also fault tolerance, like some clusters might fail. So what we basically published at ICML recently at a AES formal workshop is some work like building on DeepMind's research of which is called DLOCO, of like distributed low communication training. And what we did is basically we scaled their research and open sourced it to larger model sizes, and created like a framework and GitHub repository to build it out. And then we're in generally doing like a bunch of other like decentralized training research, and this was one of the first ones. And to explain this one very briefly, is it's basically a local SGD algorithm that leverages two distinct like optimization processes. On the one side, kind of like an inner optimizer, and then also an outer optimizer. On the inner optimizer, it's like AdamW, which kind of like performs local updates on individual workers. And then the outer optimizer, which is SGD with Nesterov momentum, really is responsible to reduce this interconnect. So basically, this is only connecting every 500 training steps, not every training step. And you can see on the right, which is our result, that ultimately it almost converges to the centralized setting. So basically, it actually over time becomes more efficient at model size and also later into the training. And you see in a green line, kind of like the local training run, and the orange or yellow line is kind of like the baseline. So it actually converges quite nicely. And it's still not as efficient, but it's getting there. And ultimately, the goal now is like to take it to much larger model sizes. So this was like a roughly 1B model. We're taking it like to a 3B and then like 10B. And that kind of like very briefly motivates also like kind of like different AI model efforts we have. So we kind of like right now fund different models across like the foundation models and agent models and also scientific models, actually also with some collaborators at MIT. Building out like a metagenomic pandemic detection model, as well as like with other collaborators at Harvard, like some basically more efficient cell simulations. But then we're also building out general like LLMs and agent models, basically building on the frontier open models in this distributed setting. I'll skip ahead a bit. Like this slide is just meant like to a bit like motivate kind of like the case for open and decentralized AGI. And I think there's reasonable concerns, obviously, about like general AGI risks and safety and alignment and whatnot. And ultimately, I think there's some basically benefits to the open and decentralized setting, obviously mainly on kind of like access and empowerment, but also enabling actually like real alignment to end users, to different societies, to different corporations. So I think actually even though obviously it's a primary focus of like say OpenAI and other frontier models to be aligned with its users. Like I think it's arguably only very unipolarly aligned. Like it's basically rejecting a lot of answers, and it obviously is kind of like aligned in one very specific like political worldview and ideology to an extent. And for example, like China might not approve of like OpenAI's alignment, right? Or like people with specific religions. So I think the goal really is like to enable real alignment, but then also kind of like security and privacy, as well as kind of like this resilience through this openness and diversity. It's like ultimately having a multi-agent, multi-LLM world seems much safer than having like a unipolar singular world. But to jump at also then into the panel, what I would just want to share as like food for thoughts, like really on this kind of more like outlook for decentralized AGI development, even how we are approaching it, is that like ultimately technology is progressing, and I think like the goal for decentralized AI and AGI should be to make differential progress, like really to prioritize like the beneficial and open kind of like progress that benefits like human agency, and also that like solves risks. So for example, that motivates one of our focuses on biosafety. Ultimately, a lot of the frontier AI labs are worried about like the biosafety risks coming from frontier AI models. So we're basically focusing on like open source foundation models that can solve those. But I think it also motivates kind of like this defensive tech directions that ultimately you need pretty strong open like models like Llama actually to defend against the attacks from centralized closed AI models. So basically, like I think it's warranted to have a strong focus on like cyber defense, biosecurity, but also really hardening the defenses against like centralized failures. Like for example, we saw with CrowdStrike a few months ago, right? Like I think that's a good example. What I would expect there to be much more of in this kind of like centralized AI paradigm. It's like imagine OpenAI's API is plugged into like millions of use cases and apps, and their servers go down. Suddenly, all of those apps go down, and I think that's not a like very stable world. So I think ultimately it's actually quite important to have this like distributed systems underlying kind of like the future of AI. Yeah, but like I think the most important one is really the last 3 points of like value alignment and kind of like having this more polytheistic approach, where basically there's like a balance of power by avoiding too much concentrated power in the hands of any individual entity or nation state, and rather having there be like a broadly distributed kind of like access to intelligence and compute, especially as it becomes more and more important. So I think the best way to put this is really that like ultimately literally our like freedom of speech, freedom of obviously also compute and exchange is at risk in the current kind of like political paradigm and kind of like with the current discussion going on. And I think it's actually quite important to defend those and not fall into like a hyper centralized, hyper like regulated paradigm that I think really restricts like freedom of speech, but also freedom of like compute and exchange, which I think should be a thing. Like, but with that said, like we're on one side hiring for many different roles, but also we're giving out fast compute grants between like $500 to $100,000 for basically different open source AI research. So definitely check those out and feel free to apply. And yeah, with that, would love to jump into the panel.
Awesome. Thank you so much. Let's thank both of our speakers. So, okay, we already have one hand raised up, so please go ahead.
I have a general cultural question. I think everybody in this room agrees on decentralized AI, right? And if you look at it in terms of biology and engineering, ensemble systems are more robust and more resilient. How come we're still talking about this? This was known 20, 30 years ago, right? And we still have this, so I guess I'm asking the panelists to talk about how do they encounter and deal with this thing that we kind of agree that diversity, equity, and inclusion is good, but you know, there's a subcurrent in us and in society that says, no, we should have the monolithic, all-powerful system, right? And I train as a physicist, right? Grand unified theories is an obsession with physics, right? There's the one model that's going to solve everything. And so how do we deal with that? Because it's obviously a strong unconscious urge that we have to have monolithic systems.
Who wants to go for this?
I'm happy to jump in first. I have I guess two-part answer to this. I think there's two main reasons, and you'll see the bias in the first reason that I have, which is I think we need the infrastructure to build the like large decentralized kind of ensemble style systems to exist before we can actually build them. And I think a lot of the research or just R&D in general that the world does indexes towards what's available to the people at the point in time. A great example I have of that is like learned experience. During my PhD, I was doing neural architecture search work, but I couldn't get access to a cluster. So I had a workstation under my desk with 4 GPUs, and all of my neural architecture search work was done on that workstation with 4 GPUs in it, and it couldn't be done anywhere else. I had lots of techniques that I would have liked to explore, but I didn't because I didn't have the resources. And I think that's true of so many places in the world, and pushes us into these situations where we just don't end up building what we kind of all know are the better solutions just because of access reasons. I kind of caveated the obvious bias because that's the problem we're addressing. We're trying to build the infrastructure that would allow people to build these large scale, robust ensemble methods over all the world's compute instead of all these like little silos. I think the other reason I have is it's a harder one to solve, which is just that from a UX perspective, I think the centralized control over the design of a system results in a system that people want to use more readily than the kind of longer term, like more robust, maybe globally better systems. And that's how we end up in situations like Meta and Facebook dominating kind of social media, because they were able to iterate so quickly and get an interface that everybody wanted to interact with, even though we probably, a lot of people I imagine in this room kind of look at the federated approaches to social media, things like Mastodon and the Fediverse in general, and say, actually, that would probably globally be better for the world with the way it deals with censorship and things. But the UX has historically been lagged behind. It's been harder to deal with. It hasn't managed to accrue the network effects. Therefore, it can't unseat the kind of locally better but globally worse solution. And it's hard to overcome that. I think the kind of good signal we have is like open source in general. So open source has managed to push through in many situations in the past, usually over longer time periods, but built as a more robust situation or solution, i.e. Linux versus kind of Microsoft and Windows is the big example there, where gradually through time, the benefits start to kind of show through and start to take hold. And in the end, we end up adopting that system. So it's almost like inevitably we do trend in the globally better situation, but in the shorter term, we seem to end up indexing towards the locally better but globally worse solution. And so there's an optimistic kind of call to action there for, I think the open source approach will again win out in this arena, but we'll go through a period of time where the locally better kind of closed source systems will win in the short term. But the kind of future looks bright is my message.
Yeah, I fully agree with that. Like, I think also we're looking very concretely at like the current like AI landscape, right? I think the challenges really is just like the scale of like resources, of compute, of talent needed, and like kind of like to unify it in one model, right? Like it's ultimately, especially with these like scales that we are approaching, right? Like where like individual training runs will cost like $1 billion or 5 or 10 to $100 billion. It's like literally what like Demis Hassabis and the Google CEO and others like shared as like rough figures. And I think it's hard to basically donate $100 billion, right? Like for say like Meta and even for the world to basically unify and coordinate its resources, its compute, and its talent to basically have like competing effort with like say the Gemini 2030 or with like GPT 2030 as like a benchmark for the model that they will train in that year. Like I think like it's not straightforward, especially obviously because you do need to an extent the business model and the value capture to justify this kind of like upfront investment. And I think obviously they see this to an extent and be able to like distribute it to Ben's point, like through billions of users that they can tap into. So I think it will be interesting to see how it evolves, but because I do think, especially for these like frontier, like AGI, ASI level models, like it's hard to conceive of basically how do we get there, that we get to like hundreds of billions of like, or like tens of billions in incentives, but also in the necessary talent. And I think the other pieces obviously is like literally that it's starting to become like a big, obviously political issue where like potentially like nation states start getting involved and where there's like insanely strong like interest groups, right? Like like literally the big tech companies themselves, but also obviously other stakeholders in those companies that strongly lobby for kind of like the more centralized, highly regulated domain. So I think those are like all like things going through my head. Also like seeing like or hearing the different arguments from people involved is that there's different challenges. It's not just like capital coordination, it's also political.
You had some thoughts, I thought.
Yeah, I mean, one is I would love to talk more, but I don't want to take too much of the time. But if we were to drastically lower the compute process inability, right? And one of the questions to you, Vincent, is that I would love to dig a little bit more into the non-homogeneous operations, especially in the decentralized space, because our current model with the company I work with, we are able to operate only on CPUs, and we don't necessarily need GPUs or neural networks to do so. And so part of that expansion, right, if we were to, my question, I guess the panelists, if you were to start again, right, and you didn't need to build out with these large, towers of Babel for GPU cluster processing, how would you rebuild for a much more stable, decentralized network if the compute cost was much lower? The problem that we're currently yet to look at, lucky enough to look at it. So rebuild it from scratch is what I'm asking.
Yeah, I think from my side, if we were to rebuild from scratch, it's similar to how I think we should just build now. Basically, the way we should be kind of going out and doing the majority of machine learning, I think, is looking like back towards the primitives that it provides us, and then combining those primitives over distributed systems rather than centralized systems. And so I like to think about this as the kind of the core operations you would interact with persistent storage, create, read, update, delete. Like, I think machine learning essentially gives us a new set of primitives that look a bit like that, but go via models themselves. And in doing that, they just are much better at dealing with large kind of generalizable data and compressing it down into representations that can be interrogated much more easily. I think you can recreate the CRUD principles with machine learning models, with the kind of analogy of create becomes train, read becomes infer, update becomes fine tune, and delete becomes forget. And we have techniques for all of those things. Forget's a bit hard and still remains a quite active area of research that's early on. But all of the other ones, we have these base primitives, and we know we can create ensembles of kind of mini models out of the models that we create using those primitives. I think we need to lean into that and just say, okay, we have a new set of ways of interacting with data. It's much richer interaction, but it requires us to go via a model. We as humans can't interrogate the data as cleanly as we can when it's a database entry. We have to kind of go via some way of interpreting dense parameter spaces, but we have the techniques to do that. So let's just scale that up over a distributed system, instead of just vertically scaling it as hard as we can to see what's possible. And then I look at the current kind of machine learning research space, and I say, well, basically, we're just doing the tip of the spear right now. We're doing the easiest, quickest way of scaling it to see what's possible, which is how we get these really dense models. And it shows the world, hey, these representations scale up massively. Like, they're really powerful. The next step is the longer kind of build to say, how do we actually just apply this out in the world? And I think it's a slightly backward step to go back to the primitives and say, actually, we're going to scale those instead of trying to scale llama horizontally instead of vertically. Like, that was a great demonstration of scaling vertically, but actually you scale the primitives themselves horizontally in a different way. And maybe we could have done that to start, or we wouldn't have had that tip of the spear kind of exciting GPT moment, but we may have had a more robust system. And then that goes back to my answer to the previous question of, I think inevitably the world does this like centralized, locally better, high efficiency UX approach first, and then through time it does the more robust, like what's actually better for the world overall build out approach. And that's what we're seeing now. But in an ideal world, maybe we would do the more robust kind of build out first, but then I guess you wouldn't have the signal of what to build out. So maybe it just has to be this way.
I guess now we would have the signal of what to build out, but I don't want to keep it from the rest of the panel. So
I'll give a little bit pushback to Ben. So on the UX aspect, I think Apple is still winning, and they are centralized, even more centralized going, and they're creating these, let's say, control layer through App Store where they can kick anyone out or let anyone get their apps installed and so on. And the reason they are able to win, which is what you were also saying, is because of that UX. But it has been a very long time and we haven't realized, okay, maybe there is a better way.
My answer to that is, once you have that tip of the spear position, you can defend it. I don't think those defenses are net good for the world, but it is possible. And we're seeing this now with people like OpenAI going into regulatory capture for their models, because they get the market with the tip of the spear with the locally better UX, and then they have to defend that. And they use systems that don't necessarily create good for the world, but do defend their position. And I think it's the same with Apple with the kind of closed app store. There are some ways in which the curation of the app store is generally good. It creates a good situation for users. Whether or not we could envision a decentralized version of that with attestation that we think here would be globally better is a different question. I tend to think you probably could. But there's kind of good that comes with the bad there. But in the end, yes, some companies are able to defend for a longer period of time than others. I don't necessarily think that defense is good overall.
I agree. And I think like the interesting analogy is also to an extent that like the real value creation and capture like is also starting to move to almost like the app layer of AI, right? It's like it's the people that build the applications on top of all of these LLM models. And obviously like they are becoming hyper commoditized in a way where like people can just switch out for OpenAI if like a new one drops, or if Llama drops, they switch out for Llama. But ultimately they still keep the distribution, they still keep the value, and actually like obviously are not only bound to like app stores, but also like have other distribution channels. So I think it actually will be interesting to see where the actual like value capture happens. I don't think right now it looks like it happens on the foundation models, at least not like the majority of value capture. But I think that's like jury's still out. Obviously, for now, it's still a lot on the on the model layer itself.
Okay, any other questions? Okay, there you go.
I have a quick question, because at the end of the day, you need to deploy these machine learning algorithms in a NLP engine, in a machine learning engine like I don't know, SageMaker of AWS, maybe Vertex AI or TCP, whatever. Can we create a policy based on the current cost of the machine learning backends? I mean, in order to identify a potential cost reduction on the fly in real environments in real time?
I didn't understand the last part. Could you repeat it?
I mean, for example, can you create a policy in order to track the current cost of the machine learning engines in order to decide if we need to send the workload for a machine learning engine to maybe, for example, to SageMaker, or maybe to decide to change the engine to Vertex AI, for example, based on the cost?
I think I understand the question is essentially, can we automatically choose the most optimal kind of backend, I guess, for execution of the model based on like profiling that model? Is that the kind of the gist of the question? Yeah. Yeah, I think in many ways, yes. And what SageMaker and other platforms like that are trying to do are trying to make a more appropriate decision on behalf of the user as to what resources are required to actually execute their model, in the sort of shift to serverless, basically, where serverless came in for like app developers and said, okay, instead of you having to understand what VM or bare metal is running behind your kind of hosted application, just write the application and we'll handle all of that for you. There's been a bit of a kind of race to try and capture that for machine learning. It's still, in my opinion, too general purpose to have the full kind of serverless infrastructure that we have in like app development, but you can get much closer than we currently do. And yeah, that's one of the areas that Jensen's working on specifically for our infrastructure. So if you come to us with a model and you say, hey, I want to train this model for 100 epochs, we would handle how that gets deployed and over what infrastructure that gets deployed to get the best kind of efficiency for you, rather than you thinking about, well, I'm going to need 4 H100s for like a day, and then I'll need another 4 for another 4 days, or whatever else. Because actually, that's a very automatable problem once you've profiled a machine learning model, like you correctly identified. I think how you do that over existing infrastructure rather than starting from scratch with a new network is very much more where Vincent and Prime Intellect sit. We sit much lower level at the kind of hardware sort of layer and say, let's just do it over the hardware that's on the Jensen protocol, rather than say looking at SageMaker and looking at these other networks that already exist and using those. So maybe Vincent can talk more about the kind of existing networks.
Okay, thank you.
Yes. Yeah, so like not much to add. Like we similarly, like right now, even like look into this and for training, right? Even for like in our AI model code, that's right. And as simple as like, hey, we need like 16 or 32 H100s. Where are they right now in the world available at the lowest cost, right? And then like if like much cheaper ones open up, like we also like checkpoint and switch to a different location. So I think that's ultimately like really what we're building is like this orchestration on all of these different data centers.
I had one question on sustainability / energy aspect. So Vincent, you talked about the situational awareness paper. So one of the key theme in that paper is about energy, and I'm wondering how you are thinking in terms of like, is it going to increase, or is it it's not going to change, even though it's the infrastructure is decentralized, energy aspect would still remain the same?
Yeah, there's actually a really good piece I can recommend by Dylan Patel from Semi-Analysis on energy and data centers. If you Google it, you'll find it. And I think the thing is basically he's like directionally correct. Like we move to like 20% of like all of like US electricity and energy will flow towards data centers. I think like his timeline and basically what singular clusters will be able to do is overly optimistic. Like he expects like gigantically centralized clusters. So like I think 1 gigawatt or something like I don't know the exact number that he mentioned, but I think that like Dylan and others told me like that's probably not gonna happen. But I think like Elon was impressive with this cluster where he like within a day or two pulled up like I think every second gas generator of the US to power it overnight. And like people were like, hey, it's impossible to power this 100,000 H100 cluster within even half a year. And he did it in 2 weeks, just by like bringing on like a lot of like mobile gas power. But I think to your point, like really, I think the challenge that I see is that there's like a bottleneck also on the energy system, right? Like for this frontier build out, but obviously if you look at the biggest clusters, right, like from Microsoft and others, like the infrastructure build out right now is gigantic, right? It's like 400 billion plus, and a lot of it is basically co-located with like nuclear facilities, with like kind of like oil lines. So ultimately, I think like there's ways to do it. I think it will definitely become like an issue at some point, not something that we worry too much about, because that's also one theory, right? Is that ultimately the price of energy is one input, especially if margins fall of like some of this hardware. And then if energy is cheaper in some part of the world, you might want to train there, right? So I think that's like one perspective, is that some places in the world obviously have much more abundant energy at very cheap cost. So I think they will win some of the data centers if they're like regulatorily allowed to have NVIDIA data centers, right? A lot of countries also are not. So I think that those are two pieces.
And do you think it might get slightly worse with decentralized approaches, because you need to have some redundancy in compute in order to be able to centralized?
I think it's actually much better in a sense that right now we are wasting a bunch of compute, right? Like it's like if you look at every data center at every cloud, like roughly like a 30 to 50% like of the compute is just not utilized. Like, and we know data centers that we work with, they have 25,000 H100s, and we saw thousands of them idling at like very cheap costs, and people weren't even aware of some of those data centers. So it's kind of like that's really the problem we are after, is like basically fully utilizing the compute out there, right? It's like I think every GPU that is not utilized is kind of like it doesn't make sense. So ultimately, especially at these large scales, so that's really what we want to solve. So, and I think that literally can also like enable us to like make much better use of these GPUs and of this infrastructure. And yeah, like so, I think and I think you don't need that much redundancy. Basically, you are just able to train. Like it's not happening on chain where you do like multiple training runs, right? Like it's similar to a centralized setting in that sense. And obviously kind of like the interconnect isn't a crazy amount of energy. So I think it should actually save a bunch of energy.
I strongly agree with the decentralized approach actually leading to better energy efficiency. I think base like assumption, we are going to, as kind of humanity, spend a lot of energy on machine learning. It is an incredible technology. We're not going to kind of slow that down, and we shouldn't slow that down because of the massive benefits it has in basically every area of knowledge. So that is kind of the base assumption. We will spend this energy. We should spend this energy. How then are we going to most optimally use the kind of world's energy towards this? Our view is that, similarly back to the kind of way I described machine learning kind of compute as just a massive graph over the entire planet, that graph right now is too sparse, which means that there's different points of the graph which aren't energy efficient. Like, they're not the best places for us to be doing machine learning, but they are kind of siloed within our organization. So the organization will use those pieces. We think a better way of doing that is to just fill out the graph. And so that we as kind of a species can just more optimally allocate our resources. The analogy we give is to Bitcoin mining, where essentially Bitcoin mining started out where it was done on like every laptop, but then it became very inefficient to mine, cost-wise, to mine Bitcoin on a laptop because there were more efficient devices to do it on. And so through just general market dynamics, the idea of spending consumer electricity on a laptop for mining Bitcoin just fell away because it wasn't an efficient way of doing it. We moved to ASICs, which were much more efficient at doing those hashing operations. And then we moved to ASICs in places where electricity was particularly cheap. Interestingly, like green sources of electricity at the moment tend to be pretty cheap because they're in places where electricity isn't useful. So like a hydroelectric power service somewhere out in the world where nobody lives can be incredibly green and also incredibly cheap, but there's no way of transporting that electricity, or there isn't a useful kind of efficient way of transporting that electricity to places where people live to actually apply it. Bitcoin can proxy a storage of electricity in a way, but it's kind of doing it off the back of a currency that's based on speculation. Our view is that machine learning work doesn't need to be geographically located anywhere particular. It can be done in those locations, and it becomes a store of electricity in a way. So us training a model out by this hydroelectric power plant is actually a really good way of us storing electricity into the kind of knowledge work itself in the creation of a machine learning model. But there needs to be an infrastructure to do that in a globally optimal way, not in a locally optimal way, like Microsoft deciding to build a data center somewhere. It should be all the way down to the people who know how to build the electricity supplies, how to build the infrastructures that will do all the logistics of creating these data centers. And if there's an infrastructure like Jensen, again, kind of obviously biased here, that allows somebody who knows a lot about hydroelectric power to suddenly do this kind of storage process, then they will do that, and they'll do it better than somebody who doesn't know a lot about hydroelectric power. So it's about pushing the incentive all the way back to the people who know this electricity kind of generation market and allowing them to do this storage process. And in that way, we get a more globally optimal system. Because right now we're just very inefficiently doing it, essentially, because of that kind of sparse graph.
Awesome. That's a great perspective. Let's quickly go through one more question. Go for it.
Yeah, so my question is about incentive structures. I think a couple that you've touched upon are financially or monetary or like coin-based incentives, and there are other incentive structures around like computing power or access to data, or maybe staking and voting weight in some kind of voting structure. Are there any other incentive structures that you can think of that might be useful for providing incentive for doing some kind of work in a decentralized AI system?
I think the big one from my perspective is the collaborative kind of like model ownership approach, where providing the resources to the model, whether you're providing compute, whether you're providing data, whether you're providing expert knowledge in the design of the model, gets kind of recognized in this open source way, where you could have an alternative to Llama that doesn't necessarily need to be funded by some kind of altruistic benefactor. It can actually just be created by all of the participants who are required. So if you have enough people who have compute, enough people who have data, enough people who have the knowledge of building the model, you could actually go out and build a new version of Llama collaboratively because all the resources are there. We saw this a little bit with Eleuther and the kind of teams around Stability AI, but they at the time required this entity to be created and to take a load of VC cash in order to lock down the compute to do that process. What would be good is if we can have a situation where providing each of the base resources underneath is enough, and you don't have to go out and somehow collect up hundreds of millions of dollars to unlock the other resources. And I think we're actually getting to that stage. We are getting close to the point where a group of participants, if you have representation from each of those areas, could build something together where they're kind of exchanging their value in exchange for access to the whole. And that's super exciting because it actually means that we can do that kind of open source, like true open source model, where rather than it just being code that's open source, it's also data and kind of compute itself, which is open source. And we just didn't have the technical rails to do that before. So we had to hack it in with these kind of like entities that would raise a load of money and then wouldn't really be under the control of the participants. And then obviously that goes in a direction that we've seen play out. So yeah, I think that's the answer I would have. That's the incentive, is we're all building a model that we will then collectively use. And we know that it's kind of governed by ourselves as the participants rather than some entity that we have to explicitly trust because it was the only way we could build it.
Okay, does anyone have a question, or did you have one?
I messaged on LinkedIn. I think I don't want to take too much more time, even though we have such a short amount. So thank you guys so much.
Okay, one last question before you guys leave. So one thing we really wanted to cover was why now aspect of decentralized AI. And I also covered some aspects on my presentation, but why don't you guys take a minute or two each and tell the audience why now decentralized AI? Why not before? Why not later?
Yeah, from my side, the answer is pretty simple for us. It's that we just didn't have the technical solutions before. And so the why now, when we originally started Jensen just over 4 years ago, was it looks like the research is getting to the place where we can solve these verification problems and we can actually do this in a decentralized way, but we're not sure. 4 years on, the research is in that position. We can build this. This does actually work, which obviously huge kind of breakthrough and very exciting, but you need to build it. And can we build it efficiently is the current position we're in. So the why now is basically because the technology didn't exist before, and we had to have these like proxy approaches, like the centralized entities collecting up cash and things like that. Now, with certain cryptographic techniques, with game theoretic techniques, with new probabilistic machine learning checking techniques, with new distributed training efficiency techniques, we can actually envision this. It just wasn't possible before. You could have gone and done the research before, but it would have been so nascent in so many areas that it wouldn't have been clear that a combination existed to solve this. Like I said, what we saw 4 years ago was, hey, it looks like this combination now exists, but more research needs to be done to find out if it does. Now it's the case of it definitely does exist, but a lot of engineering work needs to be done to actually make it real for the world.
Yeah, it's fully agreed. And I think one perspective I would add is also on the AI kind of like research and model side, intelligence side. And obviously this field is like many, many decades old and really coming to fruition like in the last few years. And I think obviously a lot of the leading efforts, even like including OpenAI, right, like started quite kind of like with a similar and aligned almost vision into this, but then obviously shifted their perspective and their approach. And I think like this ultimately just created like a huge like basically demand for more open, more decentralized systems. And even the people involved in some of those efforts obviously voiced this very loudly, like folks like Kaparthi or Elon Musk himself, that they don't think it's like safe or like the right way to do it. And I think ultimately, like just to Ben's earlier point, like just structurally those entities aren't set up to like serve the incentives and serve kind of like the broader public well. So I think ultimately there's like a much bigger push like from kind of like the broad, like just broad society, also developers honestly, and people being involved, that don't want to keep up with like the old system and want to basically build, I think, like a much better like alternative. And obviously I think we're in the earliest innings of like how to execute and make all of this happen, right? And I think like Llama is obviously one inspiring example, but obviously also with still some of the flaws of like having a centralized tech corporation behind it that needs to justify the investment. So I think there's a lot of basically just like natural push over the last decades from like academia. And I think actually this kind of like frontier AGI efforts have only really changed that, right? Like ultimately a lot of AI progress like 5-10 years ago like happened in academia and in the open and was discussed at like in literature and at conferences. And obviously in the last 5 years, like a lot of the frontier AI labs stopped publishing their key research and started being very quiet and secretive. And I think that really created like a strong motivation and momentum behind kind of like the open and decentralized AI space.
Wonderful. Let's thank our panelists again. Rohan, do you want
Thank you.
any follow-up links?
Yeah, what a fantastic panel. Thank you guys. I'll just show the Roundtable WhatsApp, the decentralized WhatsApp chat. So in case you haven't joined this yet, I highly recommend you do so just to stay updated. Take a second to do this. Okay, and next we've got the Luma calendar. So these roundtables will be bi-weekly. We have other events coming up as well. The Luma calendar will essentially show all of our events. And if you wanted an in-person seat, this is the best way to get one. And again, thank you to all our organizers. We have a brilliant team at MIT. Some of us couldn't make it in person today, but we're all working behind the scenes to make sure all these events run very smoothly. So thank you all for attending. I'm going to stop the recording now.
Sounds good. Thank you, everyone.